In mathematics, low-dimensional topology is the branch of topology that studies manifolds of 4 or fewer dimensions. Representative topics are the structure or theory of 3 manifolds and 4 manifolds, knot theory, and braid groups. It can be regarded as a part of geometric topology. History. A number of advances starting in the 1960s had the effect of emphasizing low dimensions in topology. The solution by Smale, in 1961, of the Poincare conjecture in higher dimensions made dimensions 3 and 4 seem the hardest, and indeed they required new methods, while the freedom of higher dimensions meant that questions could be reduced to computational methods available in surgery theory. Thurston's geometrization conjecture, formulated in the late 1970s, offered a framework that suggested geometry and topology were closely intertwined in low dimensions, and Thurston's proof of geometrization for Haken manifolds utilized a variety of tools from previously only weakly linked areas of mathematics. Vaughan-Jones' discovery of the Jones polynomial in the early 1980s not only led knot theory in new directions but gave rise to still mysterious connections between low-dimensional topology and mathematical physics. In 2002, Grigory Perelman announced a proof of the three-dimensional Poincare conjecture, using Richard Hamilton's Ricci flow, an idea belonging to the field of geometric analysis. Overall, this progress has led to better integration of the field into the rest of mathematics. 2 dimensions. A surface is a two-dimensional, topological manifold. The most familiar examples are those that arise as the boundaries of solid objects in ordinary three-dimensional Euclidean space R3, for example, the surface of a ball. On the other hand, there are surfaces, such as the Klein bottle, that cannot be embedded in three-dimensional Euclidean space without introducing singularities or self-intersections. Classification of surfaces. The classification theorem of closed surfaces states that any connected closed surface is homeomorphic to some member of one of these 3 families: the sphere, the connected sum of G tori, 4, the connected sum of K real projective planes, 4. The surfaces in the first 2 families are orientable. It is convenient to combine the 2 families by regarding the sphere as the connected sum of 0 tori. The number G of tori involved is called the genus of the surface. The sphere and the torus have Euler characteristics 2 and 0, respectively, and in general the Euler characteristic of the connected sum of G tori is 2 minus 2 grams. The surfaces in the third family are non-orientable. The Euler characteristic of the real projective plane is 1, and in general the Euler characteristic of the connected sum of K of them is 2 minus K. Teichmuller space in mathematics. The Teichmuller space Tx of a topological surface X is a space that parameterizes complex structures on X up to the action of homeomorphisms that are isotopic to the identity homeomorphism. Each point in Tx may be regarded as an isomorphism class if marked Riemann surfaces where of marking is an isotopy class of homeomorphisms from X to X. The Teichmuller space is the universal covering orbifold of the moduli space. Teichmuller space has a canonical complex manifold structure and a wealth of natural metrics. The underlying topological space of Teichmuller space was studied by Fricker, and the Teichmuller metric on it was introduced by Oswald Teichmuller. Uniformization theorem in mathematics. The uniformization theorem says that every simply connected Riemann surface is conformally equivalent to one of the 3 domains: the open unit disk, the complex plane, or the Riemann sphere. In particular, it admits a Riemannian metric of constant curvature. This classifies Riemannian surfaces as elliptic, parabolic, and hyperbolic according to their universal cover. The uniformization theorem is a generalization of the Riemann mapping theorem from proper simply connected open subsets of the plane to arbitrary, simply connected Riemann surfaces. 3 dimensions. A topological space X is a three-manifold if every point in X has a neighborhood that is homeomorphic to Euclidean 3 space. The topological, piecewise linear, and smooth categories are all equivalent in 3 dimensions. So little distinction is made in whether we are dealing with, say, topological 3 manifolds, or smooth 3 manifolds. Phenomena in 3 dimensions can be strikingly different from phenomena in other dimensions, and so there is a prevalence of very specialized techniques that do not generalize to dimensions greater than 3. This special role has led to the discovery of close connections to a diversity of other fields, such as knot theory, geometric group theory, hyperbolic geometry, number theory, Teichmuller theory, topological quantum field theory, gauge theory, flow homology, and partial differential equations. 3-manifold theory is considered a part of low-dimensional topology or geometric topology. Knot and braid theory. Knot theory is the study of mathematical knots. While inspired by knots which appear in daily life in shoelaces and rope, a mathematician's knot differs in that the ends are joined together so that it cannot be undone. In mathematical language, a knot is an embedding of a circle in 3-dimensional Euclidean space, R3. 2 mathematical knots are equivalent if one can be transformed into the other via a deformation of R3 upon itself. These transformations correspond to manipulations of a knotted string that do not involve cutting the string or passing the string through itself. Knot complements are frequently studied 3 manifolds. The knot complement of a tame knot K is the 3-dimensional space surrounding the knot. To make this precise, suppose that K is a knot in a 3-manifold M. Let N be a tubular neighborhood of K, so N is a solid torus. The knot complement is then the complement of N. A related topic is braid theory. Braid theory is an abstract geometric theory studying the everyday braid concept, and some generalizations. The idea is that braids can be organized into groups, in which the group operation is, do the first braid on a set of strings, and then follow it with the second on the twisted strings. Such groups may be described by explicit presentations, as was shown by Emil Artin. For an elementary treatment along these lines, see the article on braid groups. Braid groups may also be given a deeper mathematical interpretation, as the fundamental group of certain configuration spaces. Hyperbolic 3-manifolds. A hyperbolic 3-manifold is a 3-manifold equipped with a complete Riemannian metric of constant sectional curvature -1. In other words, it is the quotient of 3-dimensional hyperbolic space by a subgroup of hyperbolic isometries acting freely and properly discontinuously. See also Kleinian model. Its thick-thin decomposition has a thin part consisting of tubular neighborhoods of closed geodesics or ends which are the product of a Euclidean surface and the closed half-ray. The manifold is of finite volume if and only if its thick part is compact. In this case, the ends are of the form torus cross the closed half-ray and are called cusps. Knot complements are the most commonly studied cusped manifolds. Poincare conjecture and geometrization. Thurston's geometrization conjecture states that certain 3-dimensional topological spaces each have a unique geometric structure that can be associated with them. It is an analog of the uniformization theorem for 2-dimensional surfaces, which states that every simply connected Riemann surface can be given one of 3 geometries. In 3 dimensions, it is not always possible to assign a single geometry to a whole topological space. Instead, the geometrization conjecture states that every closed 3-manifold can be decomposed in a canonical way into pieces that each have one of 8 types of geometric structure. The conjecture was proposed by William Thurston, and implies several other conjectures, such as the Poincare conjecture and Thurston's elliptization conjecture. 4 dimensions. A four-manifold is a four-dimensional topological manifold. A smooth four-manifold is a four-manifold with a smooth structure in dimension 4, in marked contrast with lower dimensions. Topological and smooth manifolds are quite different. There exist some topological four-manifolds which admit no smooth structure, and even if there exists a smooth structure, it need not be unique. Four-manifolds are of importance in physics because, in general relativity, spacetime is modeled as a pseudo-Riemannian four-manifold. Exotic half-4. An exotic half-4 is a differentiable manifold that is homeomorphic but not diffeomorphic to the Euclidean space R4. The first examples were found in the early 1980s by Michael Friedman. By using the contrast between Friedman's theorems about topological four-manifolds, and Simon Donaldson's theorems about smooth four-manifolds, there is a continuum of non-diffeomorphic differentiable structures of R4, as was shown first by Clifford Taubes. Prior to this construction, non-diffeomorphic smooth structures on spheres, exotic spheres, were already known to exist, although the question of the existence of such structures for the particular case of the four-sphere remained open. For any positive integer n other than 4, there are no exotic smooth structures on Rn. In other words, if n4, then any smooth manifold homeomorphic to Rn is diffeomorphic to Rn. Other special phenomena in four dimensions. There are several fundamental theorems about manifolds that can be proved by low-dimensional methods in dimensions at most 3, and by completely different high-dimensional methods in dimension at least 5, but which are false in dimension 4. Here are some examples. In dimensions other than 4, the Kirby-Siebenmann invariant provides the obstruction to the existence of a place structure. In other words, a compact topological manifold has a place structure if and only if its Kirby-Siebenmann invariant in H4 vanishes. In dimension 3 and lower, every topological manifold admits an essentially unique place structure. In dimension 4, there are many examples with vanishing Kirby-Siebenmann invariant, but no place structure. In any dimension other than 4, a compact topological manifold has only a finite number of essentially distinct place or smooth structures. In dimension 4, compact manifolds can have a countable infinite number of non-diffeomorphic smooth structures. 4 is the only dimension n for which Rn can have an exotic smooth structure. Our 4 has an uncountable number of exotic smooth structures. See exotic R4. The solution to the smooth Poincare conjecture is known in all dimensions other than 4. The Poincare conjecture for place manifolds has been proved for all dimensions other than 4, but it is not known whether it is true in 4 dimensions. The smooth H-cobordism theorem holds for cobordisms provided that neither the cobordism nor its boundary has dimension 4. It can fail if the boundary of the cobordism has dimension 4. If the cobordism has dimension 4, then it is unknown whether the H-cobordism theorem holds. A topological manifold of dimension not equal to 4 has a handle-body decomposition. Manifolds of dimension 4 have a handle-body decomposition if and only if they are smoothable. There are compact four-dimensional topological manifolds that are not homeomorphic to any simplicial complex. In dimension at least 5, the existence of topological manifolds not homeomorphic to a simplicial complex was an open problem. In 2013, Cyprian Manolescu posted a preprint on the arXiv showing that there are manifolds in each dimension greater than or equal to 5 that are not homeomorphic to a simplicial complex. A few typical theorems that distinguish low-dimensional topology. There are several theorems that in effect state that many of the most basic tools used to study high-dimensional manifolds do not apply to low-dimensional manifolds. Such as, Steenrod's theorem states that an orientable three-manifold has a trivial tangent bundle. Stated another way, the only characteristic class of a three-manifold is the obstruction to orientability. Any closed three-manifold is the boundary of a four-manifold. This theorem is due independently to several people. It follows from the Den-Licaris theorem via a Heegaard splitting of the three-manifold. It also follows from René Thom's computation of the cobordism ring of closed manifolds. The existence of exotic smooth structures on R4. This was originally observed by Michael Friedman, based on the work of Simon Donaldson and Andrew Kazan. It has since been elaborated by Friedman, Robert Gompf, Clifford Taubes and Lawrence Taylor to show there exists a continuum of non-diffeomorphic smooth structures on R4. Meanwhile, Rn is known to have exactly one smooth structure up to diffeomorphism provided N4.